All right, hello again. So we're finally going to look at something new. Maybe you skipped the last two videos. If you did, welcome to the new Keynesian model. We're going to look at the bundling firm and its role in the economy. And the role of the bundling firm is to finally confront the infinity that so far we've been ignoring. Because if we recall from our art class, we had the household, and they're going to supply labor and capital, which is going to be demanded by these firms. Okay, and there's going to be infinity of these firms. So maybe I'll draw like a stack of firms. And each of these firms, this goes on forever, and each of these firms, J, is going to produce one good, Yj. Okay, so this guy's making Yj, this guy's making his Y, this guy's making his Y, and so on. Okay, and all of them are going to have a different price, Pj, which is going to clear the demand market for all of these goods. So the question is, the firms are supplying this stuff, but who's demanding it? The modeling contrivance that we're going to use, and I want to emphasize that this is a contrivance. You could write the model, and many people do write the model, where the households directly demand all of this stuff. And you just think about demand for different YJs, or consumption of each YJ, and then the household puts them together using their own bundling. Different way to think about the model. In that model, the household goes into an infinite marketplace and picks the stuff. We're going to imagine that there's a bundler that handles this process for them. So the bundler, which I sort of think of as being like Monoprix or Franprix, they're going to go into the infinite marketplace. They're going to think about what does the consumer want. They're going to put together one basket of goods, and then they're going to sell that one basket to the household. They're going to sell the YT, which the household will demand YT for purposes CT and IT. So here's your goods market, and then here's your final goods market. And then here is our intermediate goods market. So the question is, how do we clear the intermediate goods market? So we finally have to talk about the fact that, number one, there's infinite firms, and number two, that these goods are imperfect substitutes. And the way we're going to handle all of this is by using what's called a Dixit-Stiglitz production function. This is a nice function to know about. It shows up everywhere when you want to handle, anytime a model wants to work with competitive monopolistic competition, then immediately they're going to reach for Dixit-Stiglitz. It is to competitive monopolies as Cobb-Douglas is to perfect competition. So what is Dixit-Stiglitz? It's going to be an aggregation technology, and it's going to describe how, you see me peeking, I'm peeking to make sure I don't get the function wrong. It's going to describe how the bundler puts together these different goods to the upside down. So the way I remember it is that you have 5 minus 1 over 5, that's one way, and then you have it upside down over here. And then we have infinity, that's what the integral is for. We're buying the YJTs, and then we're putting them all together using this technology, and then we're going to get just the YT, which is the final good. What is psi? Psi is the elasticity of substitution. LSTIC, elasticity of substitution between any two goods. Between any two goods. Okay, so this isn't like a hoteling model or something where there's a continuum of goods and goods over here are more similar and goods over there are more similar. No, just any two goods. So we're really making a lot of simplifications to try to get this model to be solvable, to be able to write down a solution. You might have objections to these assumptions, but if you do object, then you've got to do more math. One question is, we can think of two cases that we can plug in here. So clearly, sort of a bottom floor for psi is 1, and the top floor is infinity. Why 1? Because when it's 1, we have a hole. We have a a discontinuity. So maybe 1's a nice point to think about, and infinity is a nice point to think about because why not? So let's imagine we know that psi is going to be inside of 1 and infinity. So the question is, which endpoint represents perfect substitution, perfect substitutability? Which endpoint? So you're going to have to, so first you have to think, what does perfect substitutability mean? It would mean that you have no exponent at all, right? If my consumption function, if my bundling, well, let's think about just bundling. If I don't care what I have, I can just have -1 to good j and then just put +1 to good j plus 1. Then I'm just going to add them together. There's going to be no exponent on them. There's going to be no cost of switching between things. So I want to know which of these numbers do I plug in, 1 or infinity, to make both of these powers turn into just 1. And I hope that maybe if you think about it for a minute, you'll see that if you take the limit as psi goes to infinity of psi minus 1 over psi, it will be exactly the same as taking the limit as psi goes to infinity of psi over psi minus 1. And they will be equal to 1, right? Because imagine if you plug in like 10 million here, you get 10 million divided by 10 million minus 1. Well, the minus 1 is nothing compared to 10 million. So what you get out is 1. And as that number gets bigger and bigger, you're going to get, this 1 is going to be more and more insignificant. So you'll get to 1. And if it's 1, then you have just yjt to the 1. It's just going to be, you add up all the yjt's. So as psi gets bigger, the goods are more interchangeable. Let's write it that way. The goods are more interchangeable. So this has consequences if you ever do model calibration or you ever do model fitting. You think about how substitutable should goods be in the economy. Of course, this is all very abstract and like, who knows? Like, what should I set psi to be such that it makes sense that I can substitute between a Lamborghini and a baguette? Like, if I'm really hungry, I can sell my Lambo and then I buy a bunch of baguette. This is all very abstract, but just to know that as psi goes up, the goods are more substitutable. So maybe psi equals 1 or something is a bad choice. We want something a little bit higher. Okay, how are we going to deal with this? Enough blah, blah, blah. The bundler has this production technology. Just like the regular firms, their job is to minimize total cost subject to production. Subject to production. And we know their production function. Their production function is just the Dixit-Stiglitz aggregator. It's just yjt to the psi minus 1 over psi dj to the psi over psi minus 1. Okay, now what's their total cost? They're going to choose a yjt. So they have to choose infinity of these yjt's. And what will they pay for them? Well, for all of these infinite yjt's, they're going to pay the price pjt. So this is the total cost. This is the bundler's total cost. And this is the bundler's production function. Yep. So your job now is to pause and to form a Lagrangian. Because that's all we're going to do is we're going to form a Lagrangian. And then we're going to get a first order condition for yjt. Okay. Yeah. Have a go. I want to point out, you can of course do this problem the other way. We could also do a profit maximization. Right? We could maximize profits, which will be the amount that's actually sold which is YT, times the price of the bundler's good, which is PT, minus their total costs, which is this one here, 0, 1, YJT, PJT. And we know these two problems are equivalent. I went straight to this one, making this video, because I always do cost minimization. But thinking about it for a second and checking my notes just now, this is actually easier. Why? Because we do not care about the Lagrange multiplier for the bundler, because we know that they're in perfect competition and the price is equal to the marginal cost, and the price of the bundler, PT, is the numeraire, which will be equal to 1. So we don't have to worry about the Lagrange multiplier, so it's easier to just go straight to the maximization problem. The maximization problem is a bit more direct. So I apologize for that, but that's what I'm going to be doing in this video. You are welcome, of course, to solve this and to carry along the Lagrange multiplier. You just have to then interpret the Lagrange multiplier as the marginal cost and then rationalize that the marginal cost is equal to the price. And then it'll divide out of the equation, you'll get the same thing. Okay, so in this form, we're going to substitute the production function into here, right here. So we're going to end up with, we're going to maximize YJT, and our function to be maximized will be the aggregator, YJT to the psi minus 1 over psi dj to the psi over psi minus 1 pt minus the integral 0, 1 yjt pjt. So now we have to take the derivative of this. Please have a try. Don't be afraid of the integral. Remember, the integral is just a sum. So there's going to be infinity things added together, all of them raised to the psi minus 1 over psi. And the jth one is the one you care about. And all the rest of them will be 0 because you're only taking the derivative with respect to j. So all the other ones go to 0. You'll just have one thing with 1 power on it. And don't forget the chain rule. Okay, so what do we need to do? We take the chain rule. We start the outside. So we're going to get psi over psi minus 1 times the aggregator, yjt to the psi minus 1 over psi dj. Now psi over psi minus 1 minus 1. Let's do that maths on the sidebar. We're going to have psi over psi minus 1 minus 1, and we'll write minus 1 as psi minus 1. So we're going to have psi minus psi plus 1 divided by psi minus 1. So we'll get 1 over psi minus 1. 1 over psi minus 1 here. Now we need to take the derivative of the inside, which, like we said, this is just an infinite sum. We only care about the jth one, so everybody else is going to go to 0. So we just have to think about the derivative of this here, because everything else is 0. So we'll get psi minus 1 over psi yjt to the, so we'll write minus 1 as psi over psi, so we're going to get minus 1 over psi. PT comes along for the ride. And then here we have the same point where this is just an infinite sum. Everything's going to 0 except for j, so we only think about, there's a dj here, I'm sorry. We only think about the jth one, so we can just ignore this integral and just write down pjt. And that equals 0. So we're almost done. We see right away this cancels this. That's great. I don't like this blue so much. And now we want to do another tucking trick. We want to replace this guy with yt. So we know that yt is equal to 0, 1 yjt psi minus 1 over psi dj to the psi over psi minus 1. So we need to stare at this. We need to ask ourselves, what can we raise both sides of this to? So I want to raise this to the x, and I want to raise this whole thing to the x, such that the output is what we have right here. So what I want the answer to be is this, psi minus 1 over psi dj to the 1 over psi minus 1. And remember, when you raise an exponent to another exponent, you multiply them together. So the real question I'm asking you is psi over psi minus 1 times x is equal to 1 over psi minus 1. And what is the value of x? You should see that it is 1 over psi. So this right here is equal to yt to the 1 over psi. So we can make that substitution. We get yt 1 over psi, yjt to the minus 1 over psi, pt minus pjt equals 0. And we want to solve for factor demand. So the thing that we want to get is yjt, because that's the input factor that we're trying to solve for. So let's move pjt and pt over, and yt. So we'll get yjt minus 1 over psi is equal to pjt divided by pt times yt to the minus 1 over psi. And then we'll raise both sides to minus 1 over psi. So we get yjt is equal to, I'm going to flip with the minus sign, so I'll put pjt on the bottom. So pt over pjt to the 1 over psi yt. And there you go. So this is how we've dealt with infinity. We get a demand function for each jt. So the bundler is going to demand each good jt in proportion to the total amount that it's going to produce. And the amount it's going to choose, it's going to be proportional to the price of the good jt relative to the price index pt. And it's going to be scaled by this factor here. Yeah. So there you go. That's the factor demand. So in the next video, we will see what we're going to do with this factor demand. We need to now go back and think about how the firm is going to pick PJT. Because actually we actually know what is YJT. This is the output of the firm. And we know PT is going to be the numeraire, but we'll be able to say a bit more about it than it just equals 1 in a minute. So that's why we haven't gotten rid of that yet. It does equal 1. We're going to use Walras's law, but we're going to hold off because we'll be able to say something better about it if we hold off. Really, the thing that we know nothing at all about is this PJT. So what we need to do next is circle around and try to say something about PJT. How? We know that the firm, the intermediate goods firm, the one that actually makes stuff, not bundles stuff, is going to choose its PJT in order to maximize the total flow of profits over time. But how do they do that? So that's what we'll look at in the next video. And I just realized I made a very dumb mistake I want to fix. That when I went from here to here, I raised the wrong power. Okay, so let's fix that right now. What we had was yt to the 1 over psi. I apologize, yjt to the minus 1 over psi is equal to pjt divided by pt times yt to the minus 1 over psi. And what I just wrote was I raised both sides to the 1 over psi, which is of course wrong. You would end up with 1 over psi squared. What you need to raise it to is minus psi, not minus 1 over psi. So now you multiply together, you get 1, it cancels. So on the left you just have 1, you get yjt. And on the right, I will flip everything, and I will get pt over pjt to the psi yt to the nothing. And this is the correct answer. Okay, so I apologize for that. I had written 1 over psi here, which is totally wrong. Because we're not doing division and multiplication, we're doing exponentiation. So you have to raise it to the inverse to get it to be 1. Okay, I apologize for that.